So just before the break, we were trying to figure out how total station would give me the XYZ, or in surveying call them easting, northing elevation. And so far, you kind of learn on total station, measure slope distance and vertical angle. And if we're able to ourselves measure the instrument height, reflector height, and we are on top of a traverse point where we know the elevation, then using this math here, it can find for us the elevation of point C. Now we go to the second part of the story, which is the easting, northing. So you can see here, we're kind of splitting our three-dimensional into elevation and another dimension, which is the easting and northing. So one story and then a second part of the story. To see how total station finds the easting and northing of unknown point. In this case, what we do, we need to look from the top to what's happening between E and C. And remember, when you look from the top, I want everyone to understand, when we look from the top, we don't see the SD. The blue line, we don't see. However, what we see is the projection. Look at the name, the projection of SD on the horizontal plane, okay? Which is what we call horizontal distance. And before we switch to the other view, is there any relationship between SD and HD?
Like
Feel free to
Pythagoras,
answer. Excuse me?
like Pythagoras, we can use.
So it's using the vertical angle. If you multiply the slope distance by the cosine of the vertical angle, then we're able to calculate HD. One more time, we measure the SD, we measure the vertical angle. If we multiply the slope distance in blue, multiply by the cosine of the vertical angle, then we find the horizontal distance. Now, if I take you to the second graphics here, so simply this graphics you can generate by looking at this picture from the top, and you can see you don't see any SD. So look at this line here between this point A and point C is simply the horizontal distance. Remember, horizontal distance we can calculate by projecting the slope distance into horizontal plane. How do we do the projection? Very simple. Mathematically, we multiply the SD by the cosine of the vertical angle. Now, I want you all of you to look at this picture here, and probably it's scary, but I will show you. It is very simple. Let's see, what do we have so far and what do we want to estimate. Let me ask you, and I want some confirmation, please. If I ask you this number here and this number here, which is the coordinates easting and northing of point A, please don't forget the point A is where we have a total station on top of our traverse point. At this point of time, do we have those numbers? Yes or no?
Yes, we should.
Yes, thank you so much. You have them after you adjust your traverse. If you remember, I'll take you back to remind everyone that once you adjust your traverse, you can see every traverse points, we do have three-dimensional coordinates. And that's why anytime you see point A, you know that the H of point A and the easting and the northing, the three of them, they are known values. Next is, you remember that HD is connected to the SD and the vertical angle. So looks like also the SD is a number that we know or we can calculate. Now here is the difficult part. Anything else here is known or unknown? I'm gonna be specific, and I have a point for this question. I'm asking you, do you think the alpha AC is known or a measurement or it's unknown?
Known.
Okay, anyone else?
Sorry, can you repeat please the question?
I'm saying here, I'm asking about specifically about the alpha, and I will tell you what alpha is. But for now, think about alpha as an angle, a horizontal angle. I'm asking you now, the alpha, is it known or unknown?
Well, we have to measure it.
Measure it.
Okay, so okay, guys, listen to this, please. So I'll tell you something which is kind of will surprise you. The alpha in general, total station cannot measure. In general, total station cannot measure it until we do something. So I'm going to show you later on what do we need to do to enable total station to measure the alpha. Okay, but let's find out what is alpha. So you have here alpha AC. Anybody knows what is alpha? And if you don't know, I'm going to give you a name to remind everyone. Any help first? What is alpha AC, which I'm pointing to right now with my arrow? Did you learn anything in the first year about something called azimuth?
The distance from your northern.
So the azimuth
Coordinate?
is the. So thank you so much. It's the azimuth is the angle from the north clockwise until you hit your line. For example, look at this place. You can see here is my north. So this is the north. And again, at this point A, here is the north. So this is your north here. Okay. And we start from the north clockwise until you hit line AC, and that's called alpha AC. I will repeat my question one more time. Total station, can it directly, without any effort, can it measure alpha AC? I know the answer is very hard and it's very confusing. I'll take you slowly to the answer. So the answer is no. Total station initially cannot measure the alpha. It can only measure the alpha after we do one thing on site. I will leave this thing to the end, but for now, to finish all the mathematical work, please try to understand or think that alpha we're able to measure using total station. So please, let's make it clear for now. Let's say, you know what? Everything you see in box, it means total station can measure, and we have it as a number. For example, 200 meter, 30 degrees, and easting, northing, those are in meters. Now, remember that our objective is to find what is the coordinate. I will put it in circle. So in circle, those are unknown. Hopefully, everyone agrees. So whether the NC or AC in circle, those are unknowns. And anything in rectangle, those are measurement or known. Are you following? Am I going very fast? Take your time, look at my screen. Anything in box is measurement or known. Anything in circle is unknown. Okay? Now, I think it's not very difficult. It takes you some geometry work or some trigonometry to figure it out. Let me ask you, if I'm able to find how much this component, remember this delta E is the horizontal component of the line. If I'm able to find delta E, is it difficult to find EC? What do you think?
No, just add them.
Exactly, very simple, because you're gonna go ahead and say EA plus delta E will give you EC. And same token here, same discussion. If you're able to find the delta N, which is we call it the vertical component. So this one, or the northern component, I'm sorry, northern component. So if you add this number to NA, you'll get NC. Now, look at the geometry. So you know that this dimension, probably I'm gonna dimension it here. So the distance from here to there is simply equal to the same dimension. You can see here, huh? So simply those dimensions are equal because it's orthogonal, huh? So those number, let's say I'll call this one 1, and simply this one is also 1, okay? So those dimensions are the same. So delta E is equal to the length of this line, and remember, it's a triangle, huh? And if you use basic trigonometry, very basic. How much is the distance from here to there? Given that HD is number and alpha AC angle is a number. How can we estimate this line 1? Very simple. 1 is equal to HD multiplied by sine alpha AC, which is right here. So this dimension is HD multiplied by the sine of the angle or the azimuth AC. Okay? And I think same token, this dimension here, which is number 2, is very simple. You take the HD multiplied by the cosine of the alpha AC, you'll get this dimension. Congratulations, we're done. Because simply if you take the HD multiplied by the cosine of the alpha, we get this dimension, which is delta N. You add this delta N to NA, you get NC, same here on the E. You take the HD multiplied by the sine of the alpha, you will get delta E. You add delta E to easting of point A, you get easting of point C. So there is no magic here. And here is the set of the equation. Remember, in this equation, I simply replace back my HD. If you guys remember, I replace back my HD by the original measurement. So you can see this box here, the small box is what? What is the small box?
HD.
That's HD. So you can see, huh? There is no invention, HD. Now, there is something I said and time to show you, you know, how it works. Now, if you remember, I said azimuth, the azimuth. So the azimuth alpha AC, is it something total station without any effort? So I get my total station from the box, I level it, center it above 1 point. Right away, can it measure the azimuth? Please think twice. Now I'm telling you, I have a box, it has total station, I got my total station from the box, I level it, center it above the tripod, above the point A. Can it right away measure for me the alpha AC? Think and give me the answer, please.
No.
If you think a little bit, you will see the answer is no. Although total station, you learn that it can measure an angle, a horizontal angle. I said that in the beginning. It can measure a horizontal angle. And let me show you the difference, huh? Let me show the difference between an angle and azimuth. So let's go back to this slide here. This slide here. So yes, total station, it can simply measure, you know what, this angle, huh? It can measure this angle. So what we do is, we simply level it, center it above the point, this point here, let's say point D, and I simply shoot point A. So let's put some names, huh? I'm gonna call this point A, and then I'll call this point here point B, and this is C, and then finally this is D, okay? So I'm on top of point D, and remember, total station, how it measures the angle, to be honest, it's not super magic, by the way, it's not magic. Here is how total station measure the angle, okay? It has a compass, okay? A graduated circle, and this circle is just very accurate, and that's it. But at the end of the day, it is a graduated circle. And what happens here is, number one, you will point to point A, shoot point A, and then you take the reading on when you point to point A. Let's say the reading here is simply, let's say, 10 degrees, okay? So I shoot point A, and then the reading is 10 degrees. I'm sorry, guys, sorry, okay? And then I simply move my telescope to point C, and I had another reading here, and this reading here is simply, let's say, 100, okay? 100 degrees. And remember, just like any compass, you just take the reading here. So I'm pointing right now to the reading, huh? So the reading is here, and remember the compass has a graduation, so it's graduated this way, okay? and I took reading here 100. Can anybody tell me what is the angle between line DA and DC?
90.
Exactly. So it's 100 reading here minus reading here. Now let me ask you, a total station, it has a digital compass, which means you can set the reading at any direction to whatever you like. Let me ask you the question one more time. What if, I'm gonna delete this number here, and what if when I shoot point A, I set it to 0? Because that's something I can do easily. Just click one button and it can reset my reading. It can make 0. Can anybody tell me what should be the reading here, or what the reading you expect here on the same angle?
90.
Exactly 90. Okay, so 90. So again, you can take any two readings, or maybe you can set the first reading to 0, which means the second reading will be 90. My point here is that let's go back to our first example, okay? And let's go back to our first reading. I'm asking you, does a 10 by itself has any meaning? Like, let's say you got your total station, you level it, center it, you shoot to point A, you got 10. Does the 10 itself has any meaning? Is it angle, azimuth, anything? Is it a difficult question?
It is an azimuth.
So you're telling me that the 10 here, I'm saying I have done no effort. I just got my total station from the box. I level it, centered above point D, and I shoot point A. I took the reading 10. You're saying that the 10 is azimuth, correct?
It has no meaning. There's no reference to it. You need another number to reference it off of.
I would agree. 10 has no meaning because simply 10 is to the 0. Okay, so let's say somewhere here, this is the 0 of your compass. So that's the 0, and simply your 10 is to the 0. And the 0 is oriented anywhere on site because simply I have done no effort. I got it from the box, I level it, center it, I take one reading 10, it has no meaning. I want everyone to agree on this one. A single reading a total station has no meaning. When I take another reading, yes, I can get the difference, and the difference is the angle. Okay, now same thing here. Let me show you. Forget about the 10. Okay, so forget about the 10. Okay, so let's remove the 10. Now when I point from D to C and I took reading 100, by the same token, the 100 has any meaning?
That the azimuth is 90 for point D.
No, sir. No, sir. Like the reading, did you ever use a compass to measure angle on a paper?
Yes.
So when you measure an angle, do you remember that you had to align the first side to the 0?
Yeah.
Or maybe you don't have to. Maybe you can take any two readings and get the difference, correct? So this 100 here is reference to the 0. And remember, the 0 is randomly oriented to the site. I can tell you, you know what? If the north is here, yes, if the north by accident, the north direction is here, I'll just draw an arrow. So if the north is here, like so, the 0 is oriented to the north, and this is, let's say that's the north, then in this case, yes, true, the 100 is your azimuth. So if the 0 is oriented to the north, then in this case, your reading is as azimuth, because simply the reading is to the 0, and the 0 is oriented to the north. In this case, the reading is the azimuth. Are you following? I need some confirmation, please.
Yes.
Okay, and let's agree, without doing any effort, the 0 is randomly oriented on site, which means a single reading has no meaning. Now I'm going to show you this, the magic. How can I orient my 0 to the north? Okay, so let me show you here. So I'm going to forget about this for now. I will try to use a different place. So now I'm going to draw the circle only. So that's the circle. And let's say I have here a point, another point on site, and this point is point B. And this point here is point A, and I will move it away from the circle for no confusion. So this is the total attrition point is A, like here, and this is point B. Okay, and get rid of this. Now, in general, let's say this is the zero of my graduation. And as I said, initially it is randomly oriented. So the 0 is here. Now I'm creating my line of sight. I just point to point B, and let's say I had here a reading, and this reading is 90. Let's say it one more time. This 90 does it mean anything?
No.
No. Okay. No. Let's agree on that. Now let me ask you, and let's put some numbers. Let's say for simplicity, this one is 100, 100. So the coordinates here is 100, 100, and let's say the coordinates here is 0, 0. Okay. Now I'm asking you right now, based on the 100 and 100, 0, 0, can you estimate the azimuth? What is the azimuth of the line where the coordinates is 0, 0 at one end and the other end is 100 and 100? I just make it easy,
45.
Thank you so much. So the azimuth of this line is 45. Now, I'm telling you, can you tell me roughly where is the north here in this picture? Now you know that based on the coordinates, the azimuth is 45 degrees. Would you agree if I do this, if I do my north here? So this will be the north. Okay? Where the angle from the north clockwise to the line is 45 degrees. Okay? Now, what happens if we're able to rotate and set the reading on the line to 45? So right now, before anything, my reading without any effort. So I got my total attrition from the box. I level it, center it on point A. I shoot point B, and the reading is 90 degrees. And remember, it's a digital compass, which means I can set the reading to line B to 0 or to any number I like. I'm asking you, what if we do the magic where we simply rotate the compass so that this reading here is also 45? What does it mean? If I rotate my compass so that, remember, I'm going to say it slowly, please, one more time. I will rotate the compass so that the reading on the line B equals to the azimuth of the line. Guess what happens? It means I have rotated the compass in a way that the north is, the 0 is aligned with the north. So I can move the 0 from here to there, and this is gone, if you agree. Okay? So this process here, if you follow the discussion, it is called backside. It's called backside. And in backside, it means I have 2 points on site, and those 2 points, which is A and B, of known coordinates. And because they are of known coordinates, we can estimate the azimuth of the line. Let's say in this example, I estimate the azimuth to be 45 degrees. And simply I will rotate, or not I will, the total attrition itself will rotate the circle or the compass so that the reading on the line is equal to the azimuth of the line as calculated from the coordinates of the endpoints. In this case, congratulations, the 0 of the compass has been rotated to follow the north of the site. Now, let me show you the interesting part. What happens here if I have another point here, C? So I have here another point C after I did the backside. So I've done the backside already, and now I create a line of sight from point A to point C. My question for you is, now let's say I took a reading here at point C, and this reading is equal to 75 degrees. Now, initially when we start, the single reading has no meaning. But after I have done the backside, I'm asking you, this 75 here, what do you think? What does it represent?
Your azimuth, because it's
exactly,
referenced
sir.
north.
Exactly. Only now and only now, not before the backside. After you do the backside, then the reading has a meaning, because simply the 0 is not randomly oriented on site. However, the 0 is pointing to the north of the site. And that's why the 75 is the azimuth. And as I said, I'll take you back now to our math. Initially, when I discussed this, what I did is I said, you know what? Please, for now, think about the azimuth alpha can be measured by total station, but now I can say it explicitly. So in general, or initially, total station is not able to measure the azimuth until you do something called backside process. And the backside is something very simple. You have 2 points on site, 2 control points, like a traverse point, where you know the coordinates at the end of the line. And from the coordinates, total station can estimate the azimuth and can rotate the compass to make the reading equal to the azimuth. From this point on, after you do the backside, any point on site, as long as you haven't moved your total station, in this case, you're able to take a single reading, and this single reading is going to be the azimuth of the line. Is that clear for everyone? I need confirmation, please.
Is that north arrow, is that like actually true north, or is that just a reference point you made for on the site?
You kind of make like so many terminologies. You said true north, and you said, so this is different discussion. This is your north, whatever your north is, and it's a different discussion. North is a reference line. It can be local. It means like what you did in first year. You take a first line in your traverse, and you say, okay, here is my north. This north called local north. It's arbitrary. It's something you consider, and everything comes relative to this north. But in surveying, there is more to that. There is something called the magnetic north, and there is something called the true north, which is pointing to the North Pole, which is a different discussion. For this discussion right now, the north is whatever you establish your coordinate system relative to. Is that clear?
Yep, that answered it. Thanks.
Thank you so much. Okay, any questions so far? Okay, you guys are very quiet class. I need some interaction, because really this is what gets you into me, and me into you, right? Like if you stay quiet, I would kind of assume that, you know, anyway, try to interact, please, as much as you can. Now, just before we leave this discussion and take you to another discussion, which is, let's look at the equation one more time in terms of math. Now, anybody knows what is the range of the azimuth? It can vary from what to what range? Can anybody give me the range of the azimuth angle? Like, for example, is it from 0 to 90 or from 0 to 180? Can anybody give me the range?
0 to 720.
From what?
0 to 720.
720? I think if I remember correctly, it's 360, yeah? So one full cycle, one full rotation is 360 degrees, okay? So the azimuth, the range is from 0 to 360 degrees, okay? And you say, some of you will say, you know what, Tahir, the equation that you did is simply applies only, because I'm saying here, EA plus everything is plus. However, some of you may think, what if my line AC goes here? What if my point C is here? Or maybe what if my point C is here? Or what if my point C is here? Some of you will say, you know what? No, those signs here probably will change depending on the quadrant. Would you agree or disagree?
Agree.
Okay, so I disagree myself, okay? You don't have to change those signs, and I'll tell you why. Because of the same reason. If you know about math and you have a really good math background, you will know that the sine and cosine of those terms here, those are smart. So if your angle is from 0 to 90, what happens is both those numbers will be positive. So the sine of any angle between 0 to 90 is positive. Any angle from 0 to 90, the cosine is positive as well. You guys agree? Anybody study math classes? Sine and cosine from 0 to 90, both of them they are positive. Excuse me?
I agree with you.
Okay, how about if in the second quadrant, where the azimuth is from 90 to 180. Okay, guess what? The sine is positive and the cosine is negative, which means the cosine 135 degrees, it will simply reverse and change the sign, which means, guys, bottom line is, I don't want to make it long, please do not ever change those sign based on the quadrant. All you have to do is just plug in your calculator the sine, the angle, and the sine will take care of that. Hopefully everyone is clear. Now, I'm gonna take you to another discussion right now, which will take us probably to the end of the class, which is when you read this document, please, I'm preparing this document for you as reference material. It's available on the D2L. So please spend some time to read, because otherwise there is no point of this material. Huh? So read the material and you will see Total Station was born in 1971. So almost 50 years old today. And simply as anything in my life or in our life, if you look at a cell phone 20 years ago, you will see a very basic yes or no. And if we have a light flash, that is wow. Okay. Today, those cell phones, they do so many things. Same as Total Station. The electronics and everything has changed, and that's why over the years, Total Station has gone through tremendous changes and improvement. I will show you right now few different type of Total Station that simply use the art of technology. Okay, so I'm gonna start here with something called motorized Total Station, and you will see something different from what you've seen probably last year. Okay. I don't know the link. I need to edit and select. Okay, so you know what? I will just switch to my. That's not really nice. Let's see. Please be patient. I'm going to go to my WinWord. Okay. Here we go.
So are you supposed to have a audio?
Yes. Just give me a second here. I think so. Like I'm sharing my my audio. That is what I did before and supposed to stay the same. Just give me a second here. I don't know what's happening with the hardware, but oh, there is a stop. Oh yeah, it says I have a problem. So I'm sharing my audio, but again, the system maybe is down right now. So let's see if it's gonna fix soon, huh? I think that's enough from this video. Really, what I want you to take from this video is this motorized total station. If you remember how normal total station would work, the control of the motion, whether the horizontal motion or the telescope up and down, completely controlled by the user. Like with your hands, you can rotate your whole thing left and right, and also you can rotate the telescope up and down until you create what we call it line of sight. Okay. This motorized total station, it has a servo motor. So the servo motor, you can allow it to control total station, where on the screen you can simply mark one area of interest, not a specific point, an area of interest. And this area of interest can be a connection, like steel connection, or it can be a soil, like a dirt pile. And once you kind of mark on the screen the area of interest, total station will go driven by the motor and go up and down and rotate until it scans the entire area of interest. That's one thing. The other thing is probably you've seen a couple of different, I would say, capability of total station. Number one, I think there was a connection in a bridge where you can rotate and render. This is something was not even possible years ago. You have to get the data into total station and then render it using your laptop. Right now, the processor on total station became very, very powerful to the point that you can do so many things on board of total station. Number two is when you look at the last part, when it comes to this part here, do you remember, you look at this application here, where total station is able on site to give you the volume of fill. So you have a dirt pile and you did the scan, and on the total station, you can run a calculation that was never been able to do that back in the time, except when you transfer the data into a laptop. Right now, you can do very complicated process on total station. This is really what I want to take from this video. Okay, now let's move on to another video. Okay, so I have another type of total station, which is called robotic total station. Okay, please watch this. Okay, so this video is about a total station that is simply unlike what you did last year. So last year, if I want to ask you one question, last year, do you remember how many individuals will need to operate, the minimum will need to operate total station? Like, you need one or two or three or four minimum? Any help? Two. True. So we need two individuals. One is a surveyor and the other one is a helper. Surveyor will be on the total station and the helper will carry the prism all around. So that's true. But did you notice in this video how many did we use, or the operation of this special total station? How many? Is it one or two?
One.
Only one person, and the person, this person, he is simply the surveyor and the helper on the same time. I want to remind you the total station needs leveling and centering. So even it's a robotic total station, very expensive, very complicated, but still you need to level and center above 1 point. Please don't forget that. Number 2, do I need a backside? I'm asking you something that we said it a few minutes ago. Backside. Do I need that for robotic total station or no? No. It is very smart. It can know everything. What do you think?
You need a backside.
Exactly. So remember, even it's a very advanced, very expensive, but still you have to do a backside. So what happens here is my helper and same person who is the surveyor will start a total station site, will level it, center it, do the backside. From this point on, no need for anyone on the total station site. The same surveyor will go to the other side, to the point to be surveyed, and he holds up the prism, okay, the prism. And then the total station, just like most of the things right now, I think if you have a camera and you're taking a picture for some of your friends, it will draw a box around faces, around their heads. Yes or no? Yes. Because simply right now, we have computer vision, we have image processing, and we can identify things in the image. Computers right now are very smart. If you are using Google to save all your images, do you know that you can name in one photo one person and simply the system will find the same person in 1,000 images? Anybody use this feature? Like facial recognition?
Yes, I do.
Okay, so great. So you can see the total station has a computer and it has a camera, and this camera is continuously taking photos and sending photos to the brain of the total station and locating the prism. Whenever the prism moves, then total station will track and follow, because simply same, it has a motor. So the motor or servo motor will give command and will like move left or move right. Telescope will move up and down and keep track of the prism. Given that the prism is not really running, so if the surveyor runs, like keep running, it means very fast, then maybe we lose track. So then we have to do the tracking again. But once the total station looks into the prism, then it can follow the prism. When the surveyor arrives to a point of interest, for example, I want to find my coordinate here like XYZ, then the surveyor has a controller, and the controller, it's attached to the rod. He will say, okay, you know what? I am on top of a manhole. So here is my point description. Survey me now. It is not really continuously getting coordinates. Whenever the surveyor needs, then total station will record, because there is a continuous communication between the surveyor and total station. Really, my point here is that there is a prism, and this prism in my slide right now, I want everyone to look at my slide right now and look at this prism. Is that similar to what you have seen last year or last semester? Have you seen this prism before? I don't think so, because this prism here, kind of a special prism, and it's expensive, and we call this prism 360 degrees prism. And this prism is simply used with robotic total station. And I will share with you how. Let's watch the video quickly one more time to see why this prism is very special and is being used with robot total station. I'm asking you here, do you think that this surveyor is even paying attention to where the prism is oriented? Did you notice that? When he moves between points, does he even care or look at the prism where the prism is pointing?
No.
No. And in the one that you've seen last year, it's a prism and it has a plastic enclosure. In this case, if you by mistake or not paying attention, not really pointing your prism to the total chain, does it take a measurement? No. Okay, so this prism here is designed so that no matter what is the orientation of the prism, total station can simply take the measurement. And that's why it's called 360. So if my line of sight coming from any direction, you can still take the measurement. And why is that? Why it's very convenient for this kind of application? Please watch what's happening right now. So the survey right now is simply on top of one point of interest, and he's using his data collector to communicate until the total station take a measurement now. And he is not really paying attention to what is the orientation of the prism on top of his head. It is very difficult to use a normal prism with total station like that, because simply the surveyor will have to, every time before he gets the measurement, he has to look up and make sure that the prism is pointing to total station, which is not really, it's a headache. And that's why this prism is to be used with robot total station. Now let's look at the last type of total station. I think this will conclude our discussion today. Okay, I'm gonna stop in here, and I think that's enough from this video. Really, what I wanted to take from this video is total stations right now, they have two operational modes. They can work in a reflector mode where there must be a reflector to reflect the signal back and find the distance. And there is a reflectorless mode where you don't have to have a prism on the other point. Really, it's very handy, and you can see from this video that we can measure points which is inaccessible. Look at the name, inaccessible. Very hard. Look at this. In this picture here, you can see there is a cable, like power cable, which is impossible to send someone with, or even unsafe to send some prism to this point. And once the point is close to the total station and the range is 100 meter, so within 100 meter, I can find XYZ without having to have a prism. If you have a prism, then we can measure distance up to 4 and 5 kilometers. And sometimes I can tell you, in mining application, like if you have a tunnel or mine and you want to find XYZ on the surface of the mine, it is impossible to send the prism to these points. And that's why the reflectorless mode is very handy for mine and tunnel survey. Guys, this concludes our class today. Do you have any question? Okay, if you have no question, I will wish you to have a fantastic day. Thank you so much. Bye for now.
Thanks. Have a good weekend.
You
Thank
too.
you.
Thanks.